Okay, so welcome back, everyone. It's my pleasure to introduce Kyunghyun Cho. So unfortunately, Cho could not be with us here in person today, so we'll be giving a remote talk. And well, Cho is currently a professor at New York University. He's also a director at a company within the Roche Group that focuses on machine learning for drug discovery. And he has a very distinguished career with contributions to machine learning and NLP. He has, for instance, been program chair in NightClear, NeurIPS. So we also had the pleasure to host the show several times here in the summer school. And here today, he'll be giving some insights into direct preference optimization. So let's give him a round of applause. And Shaw, feel free to start.
Okay, thanks for the generous introduction. And then sorry that I couldn't make it there in person. I would love to. At the end of the day, I still am wearing the t-shirts from the last year, but next time. So today I thought I'm going to just talk a bit about some of the things that I myself, as well as my students and my research group, have noticed about the so-called direct preference optimization that has become one of the de facto methods for fine-tuning these large-scale language models based on the binary preference data that is much easier to collect, well, at least that's in principle, than the true answers or the numeric, let's say, ratings. And then it's going to be very, very casual talk. So if you have any thoughts or the feedback, I'm very happy to hear about them as I give a talk today. And in fact, this talk is going to be based on two papers from my research group recently, as well as my two blog posts as well. So you cannot get more casual than that. So I heard that you have already learned about the language models from the distinguished speakers and lecturers there. And in particular, I heard that you may have already learned from the Slav Petrov about how to build a large-scale language models that are commercially available, for instance, the Gemini models. And then one of the things that has made a big difference between the language models that were trained in academia or in the companies, let's say labs, versus the language models that have been deployed and based off of which the companies were collecting data is the possibility of using the feedback data. So if you have used or if you're using ChatGPT, whenever you have a response from the ChatGPT, under the response you see the button, and that the button actually tells you or allows you to give the feedback on whether the response is good or not. And also there's another button that allows you to get another response from the same model. And then based on what you do and then based on when you stop and then continue your conversation, it's very easy for OpenAI or many of these commercial vendors to be able to collect this kind of binary feedback. So given these two responses to the same query X, let's say Y and Y prime, which one is better than the other? It doesn't really tell us anything about how much better or whether absolutely how good each of these responses are. However, it tells us that, okay, Y is going to be better than Y prime. And then because it can be collected relatively easily by the actual users of the services, this is very different from collecting the true answers from the annotators. Because those people who know the true answers or who are willing to give the true answers are not going to be the users of these services, but more like the employees or the contractors who are contracted and receiving money from the services to provide the answers. Now then the question is, given this kind of, let's say, triplets that we have, that is query, that is X, and then positive response, Y, so this is a desirable one between these two, and the negative response, Y prime, what is the right way to train this model? Now, more earlier, as in, let's say, 3 or 4 years ago, people are all using so-called RLHF, reinforcement learning from human feedback, or yet more technically, people were feeding a reward function on these implicit pairs of the examples, and then training a language model based on a policy gradient method such as the PPO. So all fine, but more recently, what people started to do, starting from the last year, is to use what they call as direct preference optimization. In fact, direct preference optimization is a bit of a misnomer because I don't know. Well, I don't know what the direct means there. But this is not the new idea, but this is the idea that has been used ever since around 2006 or 7 to train language models. In fact, one of the best, the Test of Time award from the ICML 2011 or 2019, that was on the natural language processing almost from scratch. There is a big section that talks about this kind of ranking or the pairwise ranking loss, and then the advantage of using this again over the log likelihood loss. Now, what you're seeing on the screen is the loss function for this loss function for direct preference optimization. And then there are a few terms here, but the most important thing is that this loss is going to go down if the probability assigned to the desirable response goes up. And then this loss is going to go down if the probability assigned to the undesirable loss goes down. So that's the only thing that you need to know for now. And then it's been massively successful. A lot of people use them. Now, is this really better than using PPO plus the learned reward function? There's a bit of a debate, there's a mixed, let's say, outcomes, but this is one of the things that are being widely used nowadays. So let's rearrange the loss, some of the terms within this loss function, and then let's look at this loss function a bit more carefully. So as I said earlier, this loss, let's say DPO loss, is going to go down when the probability or the log probability assigned to the correct response goes up, and then it's going to go down if the log probability assigned to the undesirable response goes down. Now, interesting thing is that there is yet another term that is based on P0, which I'm going to refer to as a reference model. So reference model can be anything, literally anything. Of course, we don't want to set the reference model to be uniform because they cancel out, they just disappear completely. But this is another model that we believe is reasonably good, but not perfect. So you can think of this as our prior belief over the answer distribution. And then what you see is that this is a constant with respect to the parameters. And then this constant term can be computed a priori offline over all the training examples that you're going to use. And forgetting about the terms inside this, what you're seeing is that this DPO loss is really nothing but a typical log loss that you may have learned from the machine learning 101. This is a kind of, let's say, one of the first 3 loss functions that we teach at the Machine Learning 101 course. The first one is a 0-1 loss to introduce a perceptron. Second one is the margin or the hinge loss in order to introduce support vector machines. And then third one is a log loss that allows us to introduce a logistic regression. And then what you see here is that this constant term is going to tell us about the shift in the input in this log loss function. And then this is how the log loss actually does look like. So then let's think about some different cases. All right. So what if the reference model or the prior model P0 is correct? So what it means is that the probability assigned to the correct or the more desirable answer is going to be greater than the log probability assigned to the less desirable answer under or by this reference model. So what that means is that this minus log of the P0 of y given x over P0 of y prime given x is going to be smaller than 0. And then what that means is that's going to push this whole term to the left side of this plot to the point that there is a huge amount of learning. Because you can imagine that we're going to all use the gradient-based learning because that's what we do. And then you do see that the slope on the left-hand side is extremely large. In fact, it grows further and further as we go further and further to the left. And then what that means is that if the reference model is already correct, there's going to be, in fact, more learning on P theta. And then this is a bit counterintuitive, but just, stay with me. So if the reference model that we have, that expresses our prior belief, is already correct and assigns a higher probability to the desirable answer, we're going to ensure that the learning happens more so on that particular pair. This can make sense in the sense that we are saying that we want to use the triplets that agree better with our prior belief. Now, let's look at the other way around. So what happens if the reference model is incorrect? That is that the minus log of P0 of y given x over P0 of y prime given x is greater than 0. Now we are operating on the right-hand side of this log laws. And then what that means is that there's almost no learning. In fact, it doesn't really matter what the thetas are, but the learning signal is extremely small. And then in fact, it does converge towards 0 at the exponential rate. So there's almost no learning there. So what this says is that if the collected triplet disagrees with our prior belief about how the y and y prime should be ordered, we're going to ignore it. We don't want to use that one. So you can imagine that this first term in this DPO loss is way for us to regularize learning so that the learning only happens when the examples already do agree with our prior belief that is expressed by the reference model. Still, it's a bit weird, right? So because the big question is that if my reference model is already correct, why would I actually learn it? I'm going to just use a reference model as it is. And in fact, this gets even worse because it is a common practice for us to initialize this p theta, that is a model that we want to fine-tune, with a reference model. And then this is kind of definition of fine-tuning. We start from the already trained model that was trained often with a different objective function. In the case of the language models, what happens is that we often start with a pre-training that does just a sequence level modeling, and then we're going to fine-tune it further with the so-called instruction pairs, that is the input and output pairs. So, they call it instruction tuning, but I call it just supervised learning. Do the supervised learning. And then they're going to further fine-tuning with this kind of preference-based learning. So what that means is we're going to just initialize the p theta with the p0. And if you think about it, let's go to those two cases we talked about just now. Okay, if our reference model is correct, then p theta, our model that we are tuning, is also correct initially. In other words, we are actually going to get closer to 0. So there could have been a big learning, but we're actually saying that, okay, there's not going to be much of the learning because these two terms, as you can see, if you look at this original, let's say, definition of DPO, the first term and the second, I'm sorry about that. I think that I should have actually done it better. But anyway, these two terms effectively cancel each other because we set the p theta to p0. So there's actually no learning. The same thing for the other way around. If p0 reference model was incorrect, then p theta is also incorrect, effectively pushing it towards 0. And then there's almost no learning as well. And then this is kind of weird. Okay, well, what does it mean by that? And then this actually tells us one thing, that is that we are missing one degree of freedom here. So people often use this beta. And the beta is really nothing but scaling up the y-axis. So do we want to make it at the sharper, or do we want to make it smoother? But then one degree of freedom that is missing from the original direct preference optimization is a balance between our trust in the prior, that is the trust in the reference model, and that is it, the degree to which we put the trust on the reference model. That is in fact missing. So in fact, what we noticed was that we can be much better, or we can do it much better by literally introducing one extra hyperparameter that captures this degree of belief, our prior belief. And it turned out that this is not we're not the only one who noticed this. Well, to be strict, everyone should have noticed it at the very beginning. But then people started to notice it as people use DPO increasingly more so. So the Shinake Savalo et al. Showed actually earlier, 2 months ago or some month and so ago, that introducing this extra hyperparameter allows them to control or trade off our belief into the reference model and our belief into the data itself very effectively. And then we noticed actually the exactly same thing in channel 2024 we just uploaded on archive recently. So we can introduce this gamma parameter in front of the first term, that is the log ratio or the log under the reference model, to balance between the first term and the second term. Now, one might say that, well, there are only two terms that we need to trade off, so why is it 2 degrees of freedom? Isn't it just a 1 degree? But of course, we need to think about the sharpness, right? How quickly the loss increases or decreases. And then by having this gamma, we can now control for the amount of, let's say, amount of the prior belief that we are going to impose. So, okay, this is good. So now let's see what happens with this extra hyperparameter gamma that we have introduced. So when the gamma is extremely large, now p theta, this second term, is as if it's not there at all. We don't really care. What that means is that the learning simply won't happen. It simply keeps the ordering of these responses as they are. When gamma is close to 0, which says that we are not going to put any kind of trust in our reference model, that is that our prior is that our reference model sucks. We don't care. And then that actually corresponds to having p theta being effectively uniform. Because if the p naught, p0 is, not p theta, but p0, if the p0 is uniform over all possible responses, the first term is just a log of 1, and then that's just 0. So we are effectively lowering the strength of the reference or the prior distribution we have, and then eventually when the gamma becomes exact 0, we are simply getting the rank correct. So the right, more desirable response should have a higher probability than the less desirable response. And then it's going to just learn the preference, as we would anticipate from what the name of this loss function, direct preference optimization, tells us. And then in fact, we know exactly what's going to happen and then what the exact solution or the ultimate solution should be. And then this is really nothing but just coin toss. So we are fitting a Bernoulli distribution. So for each response, we're going to look at how often y was better than y prime. Then we're going to look at how often, this is a mistake, y prime was better than y. And then we're just looking at the ratio. And then this gamma is a exponent to the ratio under the reference model. And then if our gamma is really large, the second term is ignored. If gamma is really low, only the second term dominates. Okay, so this is actually, this is not a mistake. Sorry about that. This is a flipped to say sign here. And then this actually is not equal, but it should be the proportional to. And it's relatively straightforward to show this, but this formula actually does tell us about the importance of the gamma and then why we need to have it. And in fact, we can show and then we can empirically see that the relationship between the strength of this regularizer, that is gamma, and then the distance that can be traveled when we train this model, fine-tune the reference model using DPO with gamma. If the gamma is 0, this theta, the model that we train, moves very, very far away from the reference model. However, as the gamma goes up, that is that the strength of the regularization gets greater and greater, we see that this theta of gamma, that is that the model's parameters, don't really deviate away from the origin or the initialization. There is a reference model. So this is really this is so monotonic to the point that we really didn't have to do anything. We just trained the model with the different gammas and then see what happens. And then even looking at this Euclidean distance, which is not supposed to be that meaningful in this kind of parameter space, but we do see that there is a very clear monotonic relationship between the strength of the regularization and how far away we can go from the initialization. Okay, good. And then what is even more interesting is that this gamma actually is the knob that we can use to stay in a region of the parameters where the quality of generation and the quality of ranking stay correlated. Now, this plot is somewhat complicated and very crowded. So on the left-hand side, the left y-axis corresponds to ranking accuracy. That is that how often does a model puts the higher probability on the desirable answer against the undesirable answer. And then there will be the preference. So how often does the model get the preference correct? And then the y-axis on the right-hand side is a win rate versus reference policy. Now we're going to use the GPT-4 to compute the win rate. So there's a big question I have about whether GPT-4 is the right model or is it reasonable to use it as a judge. But a lot of people do it, and then on average, on expectation, we do see that the GPT-4's judgment does correlate reasonably with the humans. So instead of going through all those human annotation, we are using the GPT-4 here. And then what you see is that as the gamma changes, depending on the strength of the gamma, the correlation between the win rate in terms of the quality of the response versus the accuracy and ranking, that is the quality of the learning the preference, in fact, has two different distinct phases, or the distinct, let's say, regions. One where the gamma is large, where there's a very clear positive correlation. But then as the gamma gets smaller and smaller, moves towards zero, we do see that there is a point at which this correlation flips. And then what do I mean by flip is that even though the model is being trained to get the ranking correct, that is to get the preference correct, but when we generate from this model, what we see is that we get a worse response in general. That's what we are seeing on the left-hand side. And the right-hand side, we still do see the correlation. And then what this really means is that it's critical for us to be able to regularize it in a proper way. Because to get to the best place, we have to set the gamma to be about 1.2 in this case of the p-theta model. But then if we set it just even tiny bit too little, then suddenly the generation quality starts degrading quite rapidly. So if you set it to 1, then that's okay. And then it turned out that the gamma, which was by default but set to 1, was relatively a lucky choice that people have been using. However, this is not the best choice at all. And what this really means is that if we want to pick the regularization strength really correctly, but unfortunately, we really cannot do this. So this blue curve, we can compute it perfectly, very easy. We can just have a held out validation examples. But the yellow curve, that is a win rate, is not easy to compute. We use a proxy that is GPT-4. However, to get the actual win rate, we need to generate it, show it to the users, and then see if the users found it better than the generation from the reference models. Now you can imagine that you can deploy it and then collect this kind of annotation. However, unless you're OpenAI, it's not really easy to get hundreds, if not thousands, if not millions of the annotations because, first of all, your users are not even going to be that many. So it turned out, unfortunately, we cannot really find such gamma in practice, as we need to perform costly evaluation of generated text on the fly. But it's really clear that the gamma needs to be somewhat large. And then, in other words, p theta, the model, must stay near the initialization, that is a reference model. And then the question is, why, right? But before answering why, I'm going to just take one quick detour to one side on trying to answer this question that has been lingering in my head for so long. Well, so long as in about a year, because DPO was only proposed last year, is that how did it work? Because this has been always a big question I had, is that you look at the DPO loss function, clearly something is missing, because especially if you start your training from the reference model, then it just doesn't make any sense because they just cancel each other. There's no learning there. But somehow it worked according to the empirical results that people have reported, and some of the models that I trained myself, both at NYU and Genentech, it kind of works. It makes it better. It makes generation better. And it turned out one of the most important thing is to train or do the fine tuning as little as possible, because that's the one way for us to ensure that the model does not deviate too far from the initialization when we use this kind of gradient-based optimization. As you may have heard, there are a number of the theoretical studies, although it's a big question whether they actually are valid in practice as well. But let's say we just believe it, then many of these gradient descent-based optimization algorithms do tend to have an implicit bias toward finding a solution that has a lower norm. But then this lower norm is often, or can be interpreted as a norm of the difference between the current model and the initialization. And then what that means is that if we only take a small number of steps, it's as if we have strongly regularized the learning to stay learning so that the parameters stay near the initialization. And then that is exactly what we see. So this is a plot that we drew exactly from one of the experiments from the previous, let's say, slide, where instead of the gamma, we're showing the number of training steps. And then what you see is that early on, that is, when we are close enough to a reference, we do see a very strong correlation between the ranking accuracy and the win rate. However, as training continues, that is that this SGD starts to moving further and further away from it, the ranking accuracy continues to get better. It gets really better. However, win rate starts to degrade. So we do see this flip of the correlation between these two. And what this actually says is that if we somehow happen to stop learning early, then DPO would look like it worked magically. And my guess is that this may be actually one of those, happy coincidence where because of the amount of the compute that is necessary to run these experiments, we tend to in fact train these models very short, in particular in academia and especially in the smaller labs. And then it turned out that that was actually a blessing rather than a curse. And then this also allows us to do this kind of analysis and thoughts. So anyway, so I'm still thinking about why DPO worked, and then one suspicion I have is that because it's from the Stanford paper, because even Stanford does not have enough GPUs, and because the conference publication cycle is too short, we actually ended up in this perfect position, perfect, let's say, region, not by choice, but by the constraints. Maybe there was a reason. But anyway, okay, so that was a bit of a side step I took. But then the big question is that the question still remains, why do we actually have to stay close to a reference model when we wanted to ensure that the preference was correctly captured, and the ranking accuracy actually tells us that it is capturing the preferences better and better as the training continues, or as the regularization lessens. So one way to think about it, I was waiting for my dinner reservation, and then I was thinking about it for a few days, and I decided to write a quick blog post. And then one thing that you notice is that the original DPR loss can be thought of as off policy, because all the answers, all the responses we look at, so y and y prime, without loss of generality, I'm going to simply say that the y is always a desirable one, and the y prime is not, because we can always flip it very easily. All these answers are from a fixed policy p theta. So let's imagine how we would collect this kind of preference annotation. You deploy the current model. You let this current model generate multiple alternatives. If the user does not ask for the alternative, you can say that, okay, so the original one was a good one. If the user selected the alternative and then came back to the original, you know that the original was good. If user chooses the alternative and then continue the conversation, you know that the alternative was better. So that's how you can actually collect this. But then the difficult thing is that because fine-tuning these models is expensive and difficult, people are going to largely fix the model to the original policy and then collect a bunch of the annotations and then use those preference annotations to fine-tune the model. So it's off policy. So in other words, the minimizing this J0, as it's called J0, this DPO corresponds to ranking Ys given X correctly for Ys that are highly probable under P0, not under P theta. And then what that means is that even though there is a pressure to assign a higher log probabilities to preferred response Y, the overall thing is all about getting the rank correct. And then there's no pressure to ensure that whatever the highly desirable, the preferred response is also highly probable under P theta. There's no reason why that would happen. Now, in a nice extreme case, that should happen. If I have an amazing table that grows indefinitely and I can save everything, then obviously I can ensure that the preferred response has the highest probability ever. But of course, we are not in the kind of idealized world. And then we actually do see that very easily. And then many of you on the audience, if you tried it out, like literally just spawn up, let's say, Google Colab or the Lightning Studio, and then try out this kind of DPO loss. And then if you track the log probabilities assigned to these responses, now you're able to look at this orange curves. What you see is that in the earlier stages, the log probabilities assigned to the preferred one goes slightly up, while the log probabilities assigned to a worse one, so there is a rejected one, goes down over time. But then, as training continues, what we see is that the log probabilities assigned to both the preferred and undesirable ones all go down. So they all start going down. Now the gap, which is what makes this log loss go further and further to the right, that is towards zero, gap grows, However, the absolute log probabilities assigned to these responses all go down together. And then this is a one clear evidence telling us that why we would see this deviation between the quality of generation and the quality of the preference learning. Preference learning is captured by this gap between these two orange curves. Quality of generation, not perfectly, but roughly corresponds to how high this orange curve is going to go up. But it goes down, in fact, by just doing a DPO as usual. And then you can find this figure in our recent paper on led by the Richard Pang and then Wei-Ze Yuan. So then, of course, one immediate thing that comes to our mind is that if the issue was because it was off policy, we probably just need to make an on-policy version, right? So instead of sampling this y and y prime from p0, we probably should just sample y and y prime from p theta, that is the current model. And then I'm going to just call it proper DPO because, the PDPO kind of, I don't know, it has a kind of nice sound to it somehow in my head. So we're going to simply use the expectation of the p theta instead of p0 in this case. And of course, this kind of online version has been always, brought up here and there. People talk about it, but then somehow no one actually wrote down the loss function. So I thought, okay, let's just write down the loss function. And then let's write down the gradient as well, because we can easily write down the gradient because this is the first thing that we, well, not the first thing, but probably the second thing that you learn in the introduction to deep learning course is it's kind of, let's say, log derivative tricks. And then using a log derivative trick and then a couple of the techniques to just derive it, it takes about 20 minutes, and then you're going to end up with the 20 mistakes, and then after you spend another 10 minutes to fix all of them, and then you end up with this equation. There's the gradient of this loss function with respect to the parameters is going to be written down as two terms. So it's the expectation over all those things that we're going to sample, but those two terms corresponds to, first one is just DPO. But this DPO is going to be on sequence pairs that are probable under p theta, not p0. And then the first term, which I think is more interesting, is the log probabilities assigned to both the y and y prime. And it's going to be modulated by how low the loss, DPO loss itself is. And then what this means is that if we do the online version of the DPO or the on-policy version of DPO, this increasing the log probability of the responses appears automatically by just defining the loss function to be on policy. And interestingly, if you read some of the papers that have been published since the DPO paper was published and now, in many papers, they do not actually emphasize this, but in the experimental details and whatnot, they almost always, not almost always, some of them talk about how it was important for them to continue to make sure that the log probabilities assigned to some of these responses are higher. And then that came as a kind of heuristics, but it turned out that what they were doing was kind of approximate version to this online version. The approximate because they don't really collect the annotations further though. So one way you can imagine is that we can just do the online annotation collection and then train it. But as I said at the very beginning, online annotation collection is very, very difficult and it's very noisy as well. So this cannot really be used, but it turned out that there are a few cases where we can use the online version or the semi-online version of this. So one such example that we actually tested in this panel 2024 is to improve the chain of thought reasoning. And then in particular for the questions where the answer can be verified exactly by simple string match. So for instance, in the simple mathematical problems, we can just look at the answer. If the answer is exactly correct, exactly same as the ground truth answer, we say correct. Otherwise, we know that it's incorrect. So in this particular case, we can be online. Now, we are not actually trying to make the response to be correct, more correct, but how the model gets to the response. We can now run this kind of direct preference optimization in an online manner to ensure that the model knows to choose the right chain of thought to arrive at the answer. So what does that mean? We have the question, and then we're going to ask the language model to answer this using this chain of thought. You could use whatever else, right? Tree of thoughts, forest of thoughts, the sea of thoughts, galaxy of thoughts, whatever. And then we're going to run it, and we're going to stop at the intermediate stage. And then we're going to continue with the couple of the other potential, let's say, outcomes. It's like the MCTS or just imitation learning. And then among them, we know which one is correct and which one is incorrect. And then we want to ensure that the continuation of the chain of thought that led to the correct one gets higher rank than the chain of thought that led to the incorrect one. So we want to lower that one. And then we can use a direct preference optimization here. However, of course, we know that the direct preference optimization alone is not enough. So we have to do some kind of online version of it. So we're going to do the online collection. And the online collection is very easy here. Now, easy, but not computationally efficient. So what we do is that we actually do it in a kind of the same delayed manner. So what we do is we're going to collect a bunch of them, train the model for some time, and then recollect this annotation, continue on. And then this is what we call iterative reasoning preference optimization. Now, it's not exactly the online version that I described to you because of some changes. One is that in this work, we only increase the low probability of the winning or the desirable responses, although it shouldn't really matter that much. And then it's not modulated by this DPO loss. Now, we tried it with the modulating with the DPO loss. It didn't really change that much because I think the DPO loss will never actually get to zero. So in a sense, it's always there. And the second thing is that we didn't use the gamma here. The reason is that these were the kind of, let's say, parallel research projects that were happening with my blog post in the middle, kind of connect them. It didn't connect enough. But then it turned out that if you do this kind of semi-online version of the direct preference optimization, we do see that it gets better and better as we continue. But it's really important to have this kind of multiple rounds of the annotation collection there. And what you see is that coming back to the original thing, what we see is that if I look at the blue curves as opposed to orange curves, this iterative online version or semi-online version does ensure that the log probabilities assigned to all these responses go up and up, while the gap, that is the gap that corresponds to pre-first learning, also continue to increase. So what does that mean? For this kind of direct preference optimization to work properly, it seems like it's really important to have some kind of oracle access to a ranking function, and so that we can minimize this online version of the preference optimization. And then this online version is really, really important because getting the rank correct or getting the rank between two examples correct has too much ambiguity. You could have these two at the very top and then get the rank correct, or you can have they can be at the very bottom and the rank is still correct. But what we need to do is that we only care about the ranks of the examples that are probable under our model, so that whenever sample from it, we're going to get a bunch of examples at the top. And then if you use a log probabilities assigned to these examples and then sort these examples accordingly, we're going to get the very best one at the very top. So you can almost think of this online version of doing so as a globally log likelihood learning is going to make sure that the reasonable ones are at the top of the chain. However, locally, this ranking loss is going to fine-tune the ranking among them so that the best one comes at the very top. So now, of course, how do we have the oracle access to a ranking function? Very difficult. Collecting data is very expensive, and then often the cheaper way of collecting data tends to come with a huge amount of noise. And in particular, when you look at the ranking of these more or less equally likely responses, small noise can break everything. So it's really a difficult problem to collect the annotation. So then, of course, we just go back to the machine learning 102, I guess, or 201, and then you think about, okay, what did we learn in the first, let's say, lecture of the probabilistic machine learning course? Is importance sampling. So perhaps we can do some kind of importance sampling. Unfortunate thing is that the importance sampling can have a very high variance, and then we can always make a low variance, a bit biased version out of it. But as you can imagine, looking at this importance weighting term, what it says is that as training continues, the y and y prime, which were sampled from the y0, that is a reference, will get increasingly less likely. And then thereby, this term actually vanishes towards zero. So unclear whether this is going to solve the problem. This is something to be checked. Unfortunately, all my students are now doing internships. So once they're back, I'll have to ask them to check it. Or maybe I should just check it myself. But I'm having fun with the vision language model this week and the next week. So maybe later. So then, whenever I talk about this, then people are going to ask me, oh, like the immediate reaction is that, well, of course, why would anybody actually use DPO? We all know that the PPO with the reward model is better. But unfortunately, that cannot be the case. And then, in fact, I suspect that there must be some other reasons why they do see a better performance out of this kind of, let's say, PPO plus the learned reward model, because the issue that we saw with the DPO, that is that the offline nature, exists exactly in the same way with the learned reward function as well. So how do people learn the reward function? That is actually to minimize this DPO loss. However, instead of using the language model to compute the score as the sum of the log probabilities of the next token, they simply have a one, let's say, regression head that's going to give us a single number. And what that means is that whatever the reward model they train will work very, very well, and perhaps only will, on the set of examples or the responses that are very probable under the reference model, not necessarily on the responses that are likely under the p theta. And then now, of course, the PPO, proximal policy optimization, does have a huge term, or the huge term that tells us that we cannot go away from the reference policy for too much. So essentially, we end up with the exactly same scenario here. Now, one may say that maybe the parameterization could be better, worse, but in general, these transformers are pretty amazing. You can learn a lot of different things. So it's very difficult for me to point to this parameterization as the cause that's going to separate out the PPO plus the learned reward model versus the DPO. But I feel like we're going to see the exactly same issue because the loss function looks exactly the same. And then if the loss function is same, it's very difficult to say that, okay, unless one of the parameterizations is completely wrong, that these models are going to have a major difference there. But who knows? It's always possible that it's easier to train a better generalizing reward model separate from the generator, but this is to be seen. And that actually concludes what I have prepared. Love to hear your thoughts or feedback, as well as any questions that I can answer. Thank you. Oops, sorry. I'll just reshare my screen. I somehow closed. Sorry about that.
So I like your comment about the amount of GPUs and time and DPO, right? And you probably now have, through the students and this work, like have first a lot of empirical evidence about how robust DPO results are. And how fast the world goes and how fast things get elevated to the best next solution, and then we don't wait enough or we don't explore enough. I personally have the impression that we might have overestimated DPO, and as you say, maybe because it's cheaper and simpler, it kind of went like a rocket. But what's your thought on that in general? Like, is DPO really, really like the way to go, or is it just like an artifact of our publish speed?
Yeah, okay. That's a trick question. I gotta answer it well enough. I'm being cornered here. Okay. So how I think about it is that this kind of preference-based learning is generally a good idea. In fact, this has been always a, kind of not debate, but more like good discussion topic that people have had for the past, let's say, decade or 2 decades or so, is that do we really care about the exact, let's say, absolute probabilities or the scores, or do we really only care about the ranking? And then generally, with the limited capacity of the models as well as the limited number of the examples, I'm on the side of okay, we only care about ranking in general. So in that sense, I think that this kind of direct preference optimization seems to be a good idea. And then my guess is that if the ranking is the only thing that we care about, and in particular the preference annotation actually says that the ranking is what we care about. We never get the precise numbers. And then we train a reward model that's going to give us some real valued reward. And then you have the PPO or any kind of reinforcement learning algorithm is going to spend unnecessary time trying to get all those at the very low, high precision, let's say, numbers that really don't matter. So in that sense, I think this kind of preference-based approach is the right way to go about. And the DPO paper kind of ignited the interest into this kind of preference-based learning or ranking-based learning. So I like it. But then has it been is this the right kind of formula that everyone needs to use? I think that's the big question. So essentially, is this the right formula? Probably not. Yeah. So that's how I think about it. Yeah.
Hi, thanks for the talk. It was really interesting to learn about this new proposed framework. And so my question is to do with the intersection of the win rate and the ranking accuracy. So that bit where the point where it intersects, is that like a sweet spot almost? Yeah, between it's like a balanced trade-off between the two.
Right. So that's a great question. So this is a sweet spot if our goal was to balance between the generation accuracy and the ranking accuracy. But that's actually not the case. Ranking accuracy in this kind of ranking-based learning is supposed to be a proxy to the generation quality. So what we want is that we want to maximize the generation quality via this proxy that is the ranking accuracy. So in fact, the true sweet spot is exactly here where the win rate is highest. But then the point here is that unfortunately, this ranking accuracy is a lousy proxy because it's only a good proxy. That is that the maximizing ranking accuracy maximizes the generation quality only in a very limited, let's say, subset of the space. And then outside that, increasing the ranking accuracy drops down. So in the sense that if these two are the things that we want to balance, then yes, sweet spot, but the true sweet spot is in fact here.
Okay, sorry. I might have missed this bit. So I was wondering, what do you define by like the ranking accuracy and the win rate? Can you just go into that in a bit more?
Oh, yes. Okay.
Sorry, yes.
So the ranking accuracy is really just binary classification accuracy. So whether the model puts a higher log probability on the desirable outcome y over the undesirable outcome y prime. And then we look at the proportion of the example over which this ordering is correct. So that's a ranking accuracy. Win rate is where the given a question, we're going to get the two answers. One from the reference model, that is a prior model PINA, and then the other is the current response or the response from the current model that is being trained. And then we should ask the humans to tell us which one is better, too expensive, too slow, and then too unreliable. So instead, because our models are relatively simple, so we use the GPT-4 in order to get this approximate, let's say, win rate. So according to GPT-4, which one of these responses is better response to the original question X? And then we look at this ratio.
Okay, that makes more sense. Yeah. Okay. Thank you so much.
Thank you.
Hi, thanks for the talk. I have a quick clarification. So regarding the gamma introduced in the first work and the NLL regularizer in the second one, do you have any hypothesis on how they are working similarly or differently in terms of moving towards the optimal policy?
Yeah. So let me actually go here. Okay. Okay. So if we are working in this kind of off policy or the offline DPO world, and then let's say we don't have access to Oracle or even an approximate way to get the annotations, then gamma is absolutely necessary because we know that this loss function is only meaningful. That is that the ranking accuracy is a good proxy to the generation quality in a very small region that is in the neighborhood of the initialization. There is a reference. So we need to have a gamma to ensure that we are staying within this region. However, if you're in this kind of on-policy world, that's not necessary, in my opinion, because all we need to do is to ensure that whatever the responses that are likely to be generated by the current model, the model being trained, their ranking is going to be correct according to this preference laws. So in the online unpolished version of DPO, my sense, it requires us to have a lot of, let's say, extra bits like the Oracle access to the annotation. But what we don't need is the gamma term. Gamma probably just zero, could be set to 0. So it's like 2 different scenarios, 2 different things we need to do in order to make it work.
Thank you.
Thank you very much for the talk. I just have a question about what you said earlier with the win rate thing, and that you said that like humans are too unreliable, too slow, etc. Like, do you think that GPT-4 is reliable in this sense? Like, have you tested like if it consistently ranks the same answers well? Like, where is this perceived notion of reliability comes from?
Yeah, that's a great question. It's absolutely not reliable perfectly. I can tell you that one. And then there's a bit of a non-determinism as well. So you're right. So the ranking between the preference between 2 responses does flip once in a while when you ask the GPT-4 exactly the same with the exactly same triplet. But what we have seen is that it's relatively reliable in a sense that the variance is much lower. So I think the right way to think about, let's say, using GPT-4 or large-scale language models as a judge is not that these language models are magical to the point that it's going to get us a better judgment than the average human does, or the on average, let's say, aggregated human rating is. That's not the case. It's impossible, right? I mean, how could that happen? It cannot do anything that is completely beyond the data. So it's going to reflect the data that is produced by the humans, largely. But what these language models do after training is done is give us a very low variance estimate of, let's say, ranking or the judgment. And then that's what I meant by the more of a reliable, as in not as in the reliable as in lower bias than the human annotators, which is impossible because human annotators, when controlled well, should have the 0 bias estimate, right? That's our target. But what we have is at the much lower variance estimator. So that's what I meant by that. And indeed, what we see is that this kind of, let's say, GPT or the language model-based judgment, for some problems, works amazingly well, has a good correlation with the human judgment, but for other problems, often that is not the case.
Okay, thank you very much.
Hi, I'm Stefania. Thank you for the very insightful presentation of DPO. I was wondering, as you initially said in the presentation, there is a counterintuitivity fact to why DPO works, in terms that you would want to penalize getting the wrong answer, not the right answer. Do you have an insight into, if we were to punish the other way around, how would you go about in order to maintain the framework that we're in, maybe with respect to the increasing the iterations or other resources?
So I mean, it is counterintuitive a bit, and in particular at this slide, it is counterintuitive because we haven't actually introduced a gamma. But once you introduce a gamma, that's actually pretty intuitive as well, in a sense that if we have a very strong belief in our prior distribution, and then our observed data point disagree with it, we should ignore it, right? Because we believe that our prior is correct. And then if the data actually agrees with our prior, then we just keep on using it. So in that sense, once we view this as a regularizer that we control the degree to which we put our prior belief on the reference model, this is okay. Now, but the biggest issue is that how much trust should we have in our prior? That's the biggest issue. And then the reason why it's difficult is, as I said, is that the gamma, this kind of strength of the regularization in this setup is really difficult to set because our proxy, that is the ranking accuracy or the ranking loss, does not correlate well with the win rate or the generation quality outside the region that is defined by gamma itself. So we do have a chicken or egg problem here. So what is the right way to do it? I'm not entirely sure. So the online annotation is always a good idea, in particular if you can actually get the actual generation quality measured on the fly. So for instance, okay, so not because some of the organizers are working at Unbabel, but the Unbabel has that quality estimation, let's say, model that is supposed to be amazing for machine translation. Then you could think about using that kind of extra quality estimation model in order to tell what is the right level of the regularization we need to use on the fly. So I don't know. I don't really have the answer to that one other than okay, we need to spend tons of money to collect more data on the fly. But what this actually tells us is that it was unintuitive, I think, because there was a missing degree of freedom in the hyperparameters. That is the degree of our belief in the prior.
Yes, thank you. And we have online Andre Martins, who raised his hand. If he can go ahead and ask.
Hey, thanks a lot for the very nice talk. It's interesting that you just mentioned quality estimation. My question was going to go a little bit around that, but so I mean, quality estimation, you can see it as like a reward model, but it might still suffer from the offline policy issue that you mentioned here. But my question was, like, there's a an alternative to fine-tuning models to align with preferences is also to change the decoding, as by modifying sampling or doing some kind of re-ranking. I would say, given what you mentioned in your talk, that maybe those issues still remain in those methods. But what are, like, from a high level perspective, what do you think could change if you could afford to do some of the work at decoding time as opposed to doing all the work during fine tuning?
Yeah, so I am actually very much on the side of that we should probably solve a lot of these problems at the decoding time already. But obviously, so the one disadvantage I think we have of using so let me put it in this way. So one advantage of training this model is actually exactly on the point that we are not using. So that advantage, actually 2 days ago, I was having a coffee with Phil Blunsom, who is now a chief scientist co-here. And then we were talking about all these things. And then one thing that he pointed out, and I totally agree with him in a sense that during the training time, our reward model or the preference model doesn't actually have to be only based on the query and desired and undesired response. We could actually add in extra information to narrow it down further. So refine this reward model much further and also make it more generalizable. Now, if you try to solve this problem in the decoding time, of course, we cannot really do that because these reward models that we use in order to choose the top one out of the, let's say, n best, generations, won't have any access to extra information. So one way I see is that what we are doing at the moment probably can be done better in the decoding time. That's my guess, because the fine-tuning takes a lot of time. Fine-tuning has actually a pretty high variance as well. If you fine-tune it over and over, you see that the variance is high. However, if we are starting to think about it more seriously, from the perspective that there are extra information that is available that we can collect during training time, to get a better, let's say, reward model or the better calibrated models to fine-tune this model, maybe we can do better by the fine-tuning rather than decoding only. Like in the quality estimation, I guess you can use the true, let's say, human translation as the input as well, I guess.
You can. I mean, if you can do it in real time, it will be,
Right.
great. But I think it might be a good alternative in the sense that if you can probably collect more frequent feedback and act on a more up-to-date model than what we can currently do with the existing techniques.
Yes, absolutely.
Okay, so let us thank the speaker again.
Oh, thank you.
Okay. So thank you, Sho, and to the participants, see you later in the evening at the banquet, okay? So we have instructions on how to get there on the website.